Hello everyone. So in this video I am going to conduct an experiment named precision full wave rectifier using an Opp Amp. First we'll go through the aim of the experiment. Here the aim of the experiment is design and verify a precision full wave rectifier and determine the performance parameter. So here we'll design the precision full wave rectifier as well as we have to verify the designed full wave rectifier. So here is the circuit diagram, that is what the design for a full wave rectifier. We used a 741 op amp, so and some 3 diodes are required here. So the input is connected to both the inverting as well as non-inverting input, and the output is taken at the CRO. So here the feedback is connected through a diode as well as a resistor 10 kilo ohm, and here we used this resistor as a balanced resistor for a non-inverting input. This was the overall circuit diagram, overall design for a precision full wave rectifier. Theoretically, so for the given input we get the output like this. For both the cycle we'll get the full for this positive half wave we'll get the positive half wave, and for the negative half wave again we get the positive half wave. This is what the output for the full wave rectifier. Okay, the same will conduct the circuit and we'll see the output of the conduction, and based on that we can verify whether my output is same as that of theoretical one or not. So here is the circuit diagram. We are connected according to the circuit diagram. So the connection is done as per the circuit diagram, and here we require a dual power supply for plus VCC as well as minus VEE, so which is given to the op amp. And here the input signal is also required. So the input is connected to a signal generator. Here is the signal generator. So the input is connected to both inverting and non-inverting input of an op amp, and the output is taken at the CRO. So here we used both channel 1 as well as channel 2. The channel 1 is connected to the input and the channel 2 is connected to the output. So as per our nature of graph, here is the input signal and this was the output signal. We got the same as per the nature of the graph. So now we'll see the performance parameter. So here we were supposed to find the ripple factor, both practical as well as theoretical. So first we'll find out the theoretical value for the ripple factor. Okay, so first we'll find the theoretical value for the ripple factor. To find the theoretical value of a ripple factor, the equation is the ripple factor is equals to Vrms divided by Vdc. So to find a Vrms is equals to Vm upon root 2, and to find the Vdc is equals to 2 Vm upon pi. So first we'll find out the Vrms and Vdc theoretical value. So Vrms equal to Vm. So initially we considered the input voltage peak to peak as 6 volt peak to peak. So Vm become V peak to peak divided by 2. So Vm will be 3 volt divided by root 2. So we get the Vrms value. So now the Vrms value is 3 volt, that is Vm divided by root 2, it becomes 2.12, and Vdc is 2 Vm upon pi. So if we substitute this value, so 2 into 3 divided by pi 3.142, we get 1.90. So this is Vdc. Now the ripple factor equation, that is under root of Vrms divided by Vdc whole square minus 1. So we will substitute this Vrms value as well as a Vdc value. So after substituting these values, that is Vrms is 2.12 divided by 1.90 square minus 1. So we'll calculate this one. We'll get the value as 0.483. So this is what the final theoretical ripple factor. So now we'll see the practical value. So after that we'll compare theoretical as well as practical value. So now we will go through the practical value. Okay, now we will calculate the practical value of a ripple factor. So here this is what my the output, full wave rectifier output. So first we'll look at the observation first. So an observation in this tabular column. So first the input voltage, initially the input is set to a 6 volt peak to peak. Okay, for this 6 volt peak to peak, the V max is V peak to peak divided by 2. We'll get the V max as 3 volt. Next VRMS, V max upon root 2. If you do V max upon root 2, that is 3 divided by pi, 3 divided by root 2. Root 2, we get 2.12 volt. So VDC, now we'll find the VDC. So here is my output. So that is full wave rectifier output. Here initially, so we set a reference line, this one, we'll set this one to a reference line here, and we'll shift the VDC from AC to DC. Here is the knob. If we shift this one, the waveform is going to shift upward. So from here to here, now we'll calculate how many divisions it is been shifted from a reference value. So here it is shifted from here to here, one division, 1 into 2. So we have connected the output to a channel 2. So here we have to consider this one. So 1 division multiplied by 2, we get a 2 volt as a VDC. Okay, so to find the ripple factor, again we have this equation, VRMS divided by VDC square minus 1 whole root of under root of this one. So already we got the VRMS value as well as VDC value. If we substitute these two values in this equation, we get the ripple factor as 0.365. So by looking at the practical ripple factor as well as theoretical ripple factor, the practical is 0.365 and the theoretical is 0.483. So these two values almost nearly equal. So when you compare these two, so my circuit is completely working as per my requirement. So this is how we can say, we can conclude that by comparing a ripple practical value as well as a theoretical value, our circuit is been verified and it is working as per my requirement. Thank you.